Hi, everybody. This is Miss Wiesen, and you are about to watch the fifth podcast in Unit 1 AP Chemistry. We're about midway down on page 12. And today we're going to talk about something called the electromagnetic spectrum. And we're going to then kind of transition into something called Coulomb's law. In the last podcast, you might have remembered me mentioning the electromagnetic spectrum when we were learning about the electron configuration of elements. So, what is this spectrum? It's basically a range of all the EM frequencies that we find in our universe. For example, the light that you turn on in your home or the sun is emitting white visible light, and that's actually only a very small part of the EM spectrum. And if you look at the handout here, you can see that it is a continuum, a long continuum of various types of radiation that contain a different frequency and wavelength. In 1864, chemist James Maxwell actually developed an elegant theory centered around this, basically saying that all forms of radiation found in this spectrum are traveling through space in the form of an oscillating wave. At one end, let's start at the right end, you have radio waves, and these are going to have the longest wavelengths with the lowest frequencies in the spectrum. In fact, the length of a radio wave is about the length of a football field. And so as you start to move left in this continuum, you're going to steadily increase in the frequency of the wave and decrease in the wavelength of the wave. And then we're going to arrive eventually at microwaves. And you guys all have heard of microwaves because you actually use this type of radiation to cook your food in a microwave. And you keep moving left, you're going to have something called IR, which is infrared waves. Now, you can't see these with your eyes, but you can certainly feel infrared in the form of heat. And notice at this point, you keep traveling left, you're increasing the frequency of the wave, and you're decreasing the wavelength of the wave, okay? And so then we arrive now at visible light, and you're going to recognize here the colors of the rainbow. You're going to see red, which, by the way, has the lowest frequency in the visible light spectrum. And as you start moving through orange, yellow, green, blue, and violet, these wavelengths shorten and their frequencies increase. Now we're into the UV portion of the spectrum, which stands for ultraviolet light. And you guys know this, it actually affects us humans. UV is very important for humans as it helps us produce vitamin D, but if we're actually exposed to too much UV, it can cause our skin to burn, and that's when we get sunburns. Keep moving left, we get X-rays. Most of you probably have had an X-ray from the doctor, or you've been X-rayed traveling through a security point at the airport. And basically, X-rays actually can pass through soft tissue, which is one reason why we use them in the medical field, and we use them to kind of visualize certain aspects internally in the human body. And then at the very end here, you have something called gamma rays, and these can be pretty dangerous and deadly to biological organisms. And gamma rays are going to have the shortest wavelength and the highest frequency of all the radiation in the spectrum. So let's go ahead and delineate and be very specific what a wavelength is and what frequency means. And so I went ahead and embedded an additional image here that you likely do not have in your notes. So if you need to pause me for a second and copy this down, then please, by all means, do. In the first image is an example of a wavelength that has high frequency. So you can see that the number of cycles that pass through that black line, which is the point we're designating, is pretty high. It's pretty significant compared to the image below. So the frequency of the image below, you can tell that the number of cycles that pass through that black line is not as much. So high frequency, meaning you have an increased number of cycles that pass through a certain point in a unit of time compared to something that has a lower frequency. Now, when we're dealing with frequency, we're going to use the Greek symbol called nu. It kind of looks like a V. It's not a V, but it looks very similar to that. And the other aspect, when we talk about radiation, the other aspect of waves that we need to consider is something called wavelength. And wavelength is represented as a Greek letter called lambda. And these two symbols you're going to use in the calculations that we're getting ready to do. But what is a wavelength? It's basically the length between two successive crests, and so, or troughs, or two identical points within that wave. So you can see the image above, very short wavelengths when we have higher frequencies, and the image below, we have longer wavelengths at lower frequencies. And so what you can then relate is the proportionality between frequency and wavelength. That as frequency increases, our wavelength decreases. And the opposite is true. All right, so really quick, I did put some definitions of wavelength and frequency in your notes. And here they are. Now, one thing before we move on and do some practice calculations with the formulas that you're going to need to know for this part of the unit is velocity. And velocity is simply the speed. So one thing to remember is that regardless of the radiation type, these waves are going to travel through space, even in the vacuum of space, at what we call the speed of light. And we denote the speed of light as lowercase c. And the speed of light is a wave that travels at 2.99 times 10 to the 8 meters per second. So it is definitely very, very fast. A couple of other things I want to point out before we move on is that wavelength is oftentimes going to be measured in meters, and frequency is going to be measured, and I actually wrote it here, it's going to be measured in hertz, is what we say, hertz. And we designate hertz as capital H, lowercase z. Now for AP Chemistry, you're going to need to know how to solve problems involving the speed of light, wavelength, and frequency of the various types of radiation that we just talked about. So right now we're going to take a close look at a couple of equations that you're going to see periodically throughout the year. Don't worry, if you pull out your AP Chemistry reference sheet, you're going to see that these two equations are given to you. So it's not like you need to memorize them per se, but you do need to know how to apply them in a given situation. So in just a second, we'll do exercise 15 and we'll do exercise 16 to kind of walk you through some expectations on the types of calculations that you would need to know using these two equations. So before we move on, let's just talk about the two equations. You have the speed of light equals wavelength times frequency. We know the speed of light. That is something we do know. So oftentimes with this equation, you'll either be asked to solve for wavelength or frequency. So you'll need to manipulate the equation to arrive and solve for the correct variable that's being asked for. And then you have this equation over here to the right, talking about energy. So we can understand more about the energy of these radiations if we know two things. H, which is something we call Planck's constant, and if we multiply that by frequency. Now, Planck's constant is a value that's given to you. It is 6.626 times 10 to the minus 34th joules seconds, okay? Joules is a unit of measurement for energy. And you can see that E equals energy, and the unit on energy is joules. And we just use a capital J for that. So let's go ahead and jump into exercise 15. And the first thing what we're going to do is follow the guess method on all of these types of problems, you guys. And the guess method is basically where you read the problem and determine what you've been given. So I'm going to make a little area over here called my givens, like the things that the problem gave me. And then from that, I hopefully can decide what my unknown is. When I know what my unknown is and what I'm trying to solve for, I can then determine what equations I'm going to use, substitute, and then solve. So the guess method. The brilliant red colors seen in fireworks are due to the emission of light with wavelengths around 650 nanometers. When strontium salts, such as strontium nitrate and strontium carbonate, are heated, this can easily be demonstrated in lab by dissolving one of these salts in methanol and then adding a little water and mixture in an evaporating dish. Calculate the frequency of red light with a wavelength of 6.0 times 10 to the 2 nanometers. Okay, so ideally, you're going to be using these two equations. And really quick, they're talking about red light with a wavelength of 6.50 times 10 to the 2 nanometers. Really quick, let's just go ahead and talk about our electromagnetic spectrum. What this problem is talking about is this visible light, the part of the spectrum that's the visible light, but more specifically, visible light right here. Right here is red part. Okay. So what do we know? What have we been given? Well, the first thing that we've been given is they gave us the wavelength, which remember is lambda. And we know the wavelength is 6.50 times 10 to the 2 nanometers, because it says that and it gives it to us. It is asking us to calculate the frequency. Well, mu is frequency, so we don't know that. That's what we're trying to calculate. And so really quick, if I go back up to my two given equations, which equation am I going to use to determine what mu is? If you said this equation, the speed of light equation, c equals lambda times mu, or wavelength times frequency, then you are absolutely correct. Why? Well, we know what c is. That's the speed of light. I'm going to go ahead and abbreviate it to 3 sig figs, 2.99 times 10 to the 8 meters per second. Okay, so really quick, before we rearrange the equation to solve for frequency or nu, one thing that I have to point out, if you look at lambda, they gave us the wavelength in nanometers. But if I look at my constant, the speed of light constant, which is c, they give it to me in meters per second. Now, we need to make sure that ultimately we're cross-canceling identical units and we're arriving at the unit we want to be in. And since we're solving for frequency, we're going to eventually arrive in hertz. And a couple of things I want to talk about just to kind of get you familiar with seeing some units that might not look familiar. Sometimes when we say hertz, so I'm going to come back up here, you might want to write this in. Sometimes hertz is, another way to say it is 1 over s, or you can do s to the minus 1. Okay. And another thing that you may need to know is that when we talk about nanometers, so a very, very incredibly small distance, that is equal to 10 to the minus 9 meters. Okay. Because right now, when I look at the value, or the unit rather, on wavelength, which is in nanometers, and then I look at the speed of light, I see meters right here. That instantly tells me that I need to get those units to line up and to match. And so the first thing I'm going to do is let's go ahead and convert wavelength, which is in nanometers. Let's first convert that to meters so our units are matching. So step one, I'm going to convert nanometers to meters. And I already have that conversion factor. I just gave it to you. And what you're going to say is you're going to start off with what you know. And you know that you have a wavelength of 6.50 times 10 to the minus 2. And if you just want to say that's, because that's also just 650 nanometers, you could just write like that and not necessarily have to do it in scientific notation. Then you set up your conversion factor, and you know that for every 1 nanometer is 10 to the minus 9 meters. Pull out your calculator, or you can move your decimal place over quite a bit, which is probably the easiest thing to do. And you'll get 6.50 times 10 to the minus 7 meters. So now I have my length units all matching. So that's the first step I'm going to do. And now let's just go ahead and solve for the problem. We know we're going to use the speed of light equation up here, but we need to rearrange that equation to solve for frequency. And so what you would easily do here, if this is the equation, to get frequency or mu all by itself, you would divide by lambda to both sides. These cancel out. So rewriting the equation, you would get frequency equals the speed of light divided by lambda. So that is the equation you're going to use. And now basically what you're going to do is, I like to say, plug and chug. And you're going to put the speed of light in the numerator. And remember, you know that it is 2.99 times 10 to the 8 meters per second. You're going to divide that by your wavelength, which we had to convert to meters. So make sure you use this one you just calculated from above, 6.5 times 10 to the minus 7 meters. Now the two cancel out. meters cancel. When you plug this in on your calculator, you're going to get 4.61 times 10 to the 14. And you can see seconds is in the numerator, but if I bring it down 1, you would have to put -1 because you're doing the inverse. If you don't like that, you can also write hertz. But I'm just letting you know this unit right here that you're left with is indeed an alternative unit for frequency when you're not writing hertz specifically, like I just mentioned above. Okay, and so you can see that our answer is matching the answer that was listed. Let's do one that's a little bit more challenging. We have a blue color, it's exercise 16. The blue color in fireworks is achieved by heating copper 1 chloride to about 1200 degrees Celsius. Then the compound emits a blue light having a wavelength of 450 nanometers. What's the increment of energy that is emitted at 4.50 times 10 to the 2 nanometers of copper chloride? So as I'm reading this, I noticed that in the last sentence, it's asking, what is the increment of energy? Okay. And if I go back up to my 2 equations that I've been given for this part of the unit, it looks like I'm going to go ahead and I will be using Planck's equation. E, in fact, stands for energy. However, there is a circumstance where I'll probably have to use both equations. And it looks like when I'm looking at exercise 16 and following the guess method, let's write our givens, I might see that I'll actually have to use both of those equations. All right, it gave us wavelength in the problem, 4.50 times 10 to the 2 nanometers of copper chloride. It's asking us to solve for E, or energy. That's why it says one increment. What is the increment of energy? So we're solving for energy. And by the way, we do know Planck's constant and we do know the speed of light. So these are 2 things that have been given to us. If you go back up, Planck's constant is 6.626 times 10 to the minus 24 joules seconds. And the speed of light was 2.99 times 10 to the 8 meters per second. Remember those constants, you don't need to memorize, they are given to you. So at the end of the day, if I write both of my equations, I'll go ahead and just port them down. We've got C equals, or speed of light equals lambda, wavelength times frequency, and energy equals Planck's constant times frequency. So at the end of the day, we were trying to solve for E. But notice in our givens, we were never given frequency. We have no idea what it is. And so, but we do know H. That's a constant that's been given to us. So we do know that. We just don't know frequency. So can you tell me what we're going to do to try to get frequency? If you look at the speed of light equation, we do know C, which is the speed of light, it's a constant. And the problem here did give us wavelength. So what I could first do is use the speed of light equation and solve for frequency, and then use that to do the second equation of Planck's constant. So this is actually a multi-step problem where you'll use one equation to determine frequency and then take that value and plug it into the second equation. All right, so let me erase this and let's just do that real quick. Remember, if you have something in nanometers and then another thing that has meters listed, you need to get them into the same unit. So again, 1 nanometer is equal to 10 to the minus 9 meters. So our first step that we're going to do, step 1, is you're going to take the speed of light equation and you're going to rearrange it to solve for frequency because, well, you were never given frequency in the problem, but you do know the speed of light and wavelength. And so I'm going to go ahead, you guys, and plug and chug. And when I did the conversion here, or I converted it to meters. So I want you, so I'll just write it. So I converted the nanometers to meters and I got 4.50 times 10 to the minus 7 meters. So then I just plug and chug. So frequency equals, let me get back into my normal color. So now I just plug and chug. Frequency equals the speed of light, 2.99 times 10 to the 8 meters per second, divided by wavelength, which I just converted out of nanometers and put it into meters. 4.50 times 10 to the minus 7 meters. I plugged this in on my calculator, you guys, and I got 6.66 times 10 to the 14. And what would the units of frequency be? You could say hertz or s to the minus 1, which is what we'll do, because, by the way, these two units canceled. Now I have frequency, so now I can determine what the energy is using E equals Planck's constant times frequency. I will need to rearrange I know Planck's constant, and now I just calculated frequency from the previous step. So I would say Planck's constant, 6.626 times 10 to the minus 24 joules per second. Multiply that by frequency, which we also just calculated in the above step. Which units here are going to cancel? S minus 1 to the S, because they're inverse of each other, so they cross cancel. Now, when I get the calculator out, I am going to actually end up arriving at this answer. And you will see that joules is the unit, and that was the only thing that had remained after I cross-canceled my units. And that should make sense because when I'm solving for energy, my unit of energy is in joules. Okay, so let's get into Coulomb's law, the top of page 14. Shout out to all the physicists out there because Coulomb's law is a big concept in physics. And if you've taken physics, hopefully you've heard it before. But Coulomb's law is actually has huge implications in chemistry as well. And you can see here that Coulomb's law is a law, and you can see it's defined by a formula we have written here in our notes. But it's used to calculate the force between two charged particles. And so let's take a look and talk about force really quick in terms of atoms. So I found a simplified model of an atom here. And one of the things about Coulomb's law that we learned in first year chemistry is that when you have two oppositely charged particles, they're going to be attracted to each other. So over here, we could just quickly write and demonstrate that. So these forces would be attractive. They are attracted to each other. Consequently, if you get charged particles of the same charge, so two protons sitting next to each other in close proximity, or even two electrons, you're going to get a force of repulsion. Now, before we go back to Coulomb's law and take a look at the formula, this is actually one of the reasons why we have neutrons found inside the nucleus. Those neutrons help buffer the repulsive effect that the protons are having on each other within that small nuclear space of an atom. And so going back to Coulomb's law, we see a formula here, and there is a typo really quick, you guys. I want you to just add this to your notes. I apologize. I didn't put down here where I'm describing what each variable is. I did not put the subscripts for the two Q's. So Q sub 1 and Q sub 2. So I'll put a star right now. If you just could go back into your notes and add those in, I apologize. So here's Coulomb's law. F equals K. And by the way, K is Coulomb's constant. Q1 times Q2 divided by R squared. And you can see below what each of those variables mean. One thing that may confuse you is when we get to Q1 and Q2 and what that really means. If you go down here, it is defined as the magnitude of charge of the first atom or ion, and that would be Q1, where Q2 would be the magnitude and the charge of a next or a second atom or ion, if you will. Now, what does magnitude really mean? Don't let the language catch you up here, guys. Magnitude just means size. So if we go down to the image below, we can kind of model that so you can see what I'm talking about. Let's, just for grins, go over here to Q1 and call it a calcium 2 plus ion. And Q2, we will make it, again, I'm just doing this as an example, a chlorine -1 ion. Between these two ions, which one has the larger size of charge? If you said calcium because it's a 2 plus, then you are absolutely right, where chlorine only has a -1 or 1 minus. So magnitude simply means size. Now let's go ahead and define how these variables are related to each other. One of the things that I want you to add to your notes is if you look in the numerator over here, you're taking Q1 times Q2. You're taking the magnitude of charges of each of the atoms. And when you see these variables in the numerator, what you can actually assume is that the magnitude, or Q1 and Q2, is directly proportional to force. So what does that mean? That means as the size of the charge increases, the force between the atoms also increases, or the force between the ions also increases. So let's go ahead and write that. And there you have it. I made a little flow chart. So to recap what I just said, the variables in the numerator of Coulomb's law, so Q1 and Q2, they're proportional to force. And so what that means is as the Q's increase, so does the force between those atoms or ions. Let's go ahead and talk about the r squared in the denominator, radius. Now, when you see a variable in the denominator, what we can say is that that variable is going to be inversely proportional to force, meaning as we increase the radius, we're going to actually decrease the force between the two atoms or ions. So let's go ahead and write that in our notes. Okay, so to recap here, the variable in the denominator, which is radius or distance between the atoms or ions, it's inversely proportional to force, meaning that as the distance between these two atoms or ions increases, the force between them decreases. So why are we learning about Coulomb's law? Because this concept, you guys, is not going to go away. It's going to be here all year. But most importantly, if we understand the fundamentals behind Coulomb's law, then what this allows us chemists to do is it allows us to make predictions about the periodic table. It allows us to understand the trends that we see throughout the periodic table. And so instead of us memorizing trends, we actually can intuit them based off of Coulomb's law. Now, later in this unit, we're going to talk about these trends that I'm speaking of. And so I needed to give you guys a good understanding of Coulomb's law, or a general overview right now, because we're going to come back to it quite a bit more throughout the year. You'll see Coulomb's law coming up over and over again. So let's go down to page 15 and just do a really quick kind of, I guess you could say, practice in understanding Coulomb's law. And what I'm going to ask you to do is for each model, we'll talk about it briefly. Please pause me and answer the questions that are being asked within the notes, and then come back to check your answers with mine. This will actually really help you understand where you're at in understanding Coulomb's law. Model 1. So right now, I see in Model 1, there are several images being drawn of a cation and an anion and a distance that separates them. And then if I move on over, I can also see that it gave me a force between them. And you guys can see here that a cation and an anion are going to have a force of attraction, which is why it says force of attraction, because the opposite charges will attract each other. And we measure force in newtons, you guys. You know, it's not incredibly important right at this moment, but get used to that. You'll see some units popping up that you may not be familiar with if you haven't taken physics. Anyway, it gives it gives an associated force of attraction in each model. And so what I want you to do is I want you to actually draw model D. And the scenario would be that model D is going to have, I want you to predict the force of attraction if there was a distance between a cation and an anion of 0.4. Okay, so take a second, draw the model in, and predict what the force of attraction would be if the distance between a cation and an anion was 0.4 nanometers. So I drew the model here, and I'm looking at the force of attraction, and as I notice that as in each image, the distance is increasing, and therefore the force of attraction between those two ions is decreasing. And so if you said the force of attraction was anything less than 0.26 times 10 to the minus 8 newtons, then you are absolutely right. Let's do model number 2. And here it's asking what's going to happen to the magnitude, so the size of the force, as you go down a group. And so you can see here in the picture of Model 2, we're in the alkali metals, and they're showing us lithium, sodium, and potassium. There's another little model down here that might be helpful, and it says that if we look at the size and the width of the arrow, then that's also indicating to us the stronger force of attraction with bigger and thicker arrows. So take a look at what's happening here. You have lithium, sodium, and potassium. So you're going down a group or a column in a periodic table. And what this is asking you is, what would the force of attraction between these electrons and the nucleus of that atom, how would the magnitude of this force change as we go down a group, rather? If you said that as you go down a group on the periodic table, the magnitude or the size of the force is actually going to decrease. And the reason is because as you are going down the periodic table, your atoms are getting bigger, and therefore more orbitals are being added to house and hold on to those electrons. And as you're adding on electrons, they're getting further and further away from the nucleus. And so those outer valence electrons, and you guys, that's what V of E minus means over here, valence electrons, they get further away from the nucleus. And we learned that as we increase distance, force decreases, inversely proportional. All right, model 3. Now it's asking for you to draw in a fourth model that we call model F, and tell me and predict the force of attraction if you were to have an image with 4 protons or 4 protons with only one anion on the other side. You can also see they give you a force associated with each image too. So predict what you think the force would be. Pause me, you try first, come back and check your answer. So I went ahead and drew in the model. Obviously, we're keeping distance constant here. So what we changed was Q. We changed the size or the number, the quantity of charges. Expect that the force of attraction between these charged particles would be greater than 6.9 times 10 to the negative 8 newtons. All right, let's take a look at model number 4. And what they're asking here is, how would the magnitude of force as you go across a period or a row in the periodic table be? And so they've showed us sodium, aluminum, and chlorine here. So this would obviously be 3 atoms from the third period, from the third row. And go ahead and pause me and predict what you think would happen here. If you said that as you go across the periodic table, you're going to actually, since you're adding more electrons into the already existing orbital, the force of attraction between those electrons and the nucleus of the atom is going to steadily increase as we go across a period. Okay, you guys, that's it for Coulomb's law for now. In our future presentation, in the future, we're going to do some podcasts that talk about trends, and we're going to do our best to try to relate that back to what you just learned here with Coulomb's law. All right, thank you so much for tuning in.